Good morning. Let's see. I'll jump right into screen 2, I guess. Which is probably not in focus. But that's okay. That looks okay. Okay, today we're going to take a look at Ampere's law, which is something kind of similar to Gauss's law, and we'll see what it looks like here. Some kind of a thing. Okay, let's start off by imagining that we have a
Did you switch to the visualizer?
I thought I did, but I probably forgot to click share. Yep, I selected it and forgot that last button click. There we go. How's that?
That's good.
Okay, and so, whoops, I wanted to stay centered on that spot there. And draw a bigger circle. And so we're going to imagine that this thing right here is a current going into the page. So and it's a long straight current. We figured out, last week, I think, that the magnetic field of such a current is this: B equals mu naught I over 2 pi r, and it's concentric circles around the wire. And so in this case, the magnetic field would actually, at some distance r out here, would actually be given by, have a magnitude of that, and it always points along this concentric circle. And what I'd like to do is integrate along that path. And the integral that I'm going to perform is going to be a line integral, and we'll put a circle on it. In the instance of Gauss's law, that circle meant that it was a circle over a closed surface. In this case, the circle is going to mean that it's over a closed loop. And the integral we're going to do is going to be a line integral. And so if you have a line integral and it's over a closed loop, then you can put a circle around it. Or when we put a circle around it, that's what we mean. Now, I'm not sure, I don't even remember if something like this showed up in mathematics, putting circles on things or not. Do you remember anything, Nolan?
I actually looked it up because I kept getting confused. The notation is really loose.
Okay.
I can't find any hard rules that are very universal at all.
Okay, I kind of suspected that. So it's just a convention adopted in physics textbooks and maybe by physicists in general. In different fields, people will adopt conventions that they just have grabbed from somewhere and just keep using them. So in this case, we're going to do this integral all the way around the loop. And if we pick a particular point, our dl will just be some short line, very short line, that's tangent to the loop at that particular point. But it will point in the same direction as the magnetic field does at that point as well. You have to imagine shrinking this thing down until it's infinitesimally long. And what you end up with in that case is that B dot dl is just going to become the magnitude of B, the magnitude of dl, and the angle between them, which is, or the cosine of the angle between them, which is 0, and the angle is 0, the cosine of 0 is 1, so it'll just be b dl. And that's what we integrate all the way around the loop. And so we'll have the integral around this loop of b dl, but I've got an expression for b. It's equal to mu naught I over 2 pi r and then dl there. Well, I picked a loop that was always the same distance away from the center of here, center of the wire, and so r is going to be a constant, this little r, and everything in the integrand is a constant except for the dl. So this just becomes mu naught I over 2 pi r times the integral of dl. And if you want to, you can think of dl as equaling r d theta. And r is again going to be a constant, but then the little length element that we have here, this could be a dl at a later point. This will be r again. And this angle, excuse me, this angle will just be d theta. And so I can pull this r outside the integral, but already what's happening is that my original expression, b dot dl, is now mu naught I times little r over 2 pi r, and the r's divide out, and now what's left inside the integral is just d theta, and you're integrating the angle theta all the way around the circle, which gives you a 2 pi. And so what you end up with is this integral ends up being mu naught I over 2 pi times 2 pi, which is just mu naught I. All right, well, that was interesting. In this case, we happen to integrate in the same direction that the magnetic field pointed. If we had integrated in the opposite direction, we would have had that dl was always pointing in the direction opposite the magnetic field. And in the dot product, you'd have the cosine, not the cosine of 0, but the cosine of 180 degrees, or pi radians, which is -1. And if you integrate in the direction opposite the magnetic field, you'd get minus mu naught I. Now, that's the case when you have, we had nice cylindrical symmetry here. We picked our path of integration to be always the same distance away from the center of the current that was carrying this, and so forth. And so we get this nice tidy expression. But it turns out you could move this wire off center and do the integral, and you'd get the same thing. You could move the wire completely out of the circle that we integrated, and if you did that, you'd end up with 0 when you integrate it around there. So this expression ends up depending on how much current you happen to have in there, and you can actually extend this idea to, first we'll draw, well, I'm just going to draw a big circle here. This will be a different circle in this case, but I can have a current over here. I can call that I1. Maybe stick a current over here, I2. This one's coming out of the page. This one's going into the page. You can scatter around in this thing a bunch of different currents. And if you integrate in a circular path around there, let's see, we can go in this direction. In this case, I'd end up with, when I integrate around that circular path, I would get that integral of b dot dl is going to equal, oh, let's see. I need to stick an R on here. Mu naught, actually, it'll end up not mattering what that thing happens to be. Let's see, if I'm integrating in that direction, currents that produce magnetic fields that are kind of in that direction will produce positive ones. If they're going opposite, like that one, it produces a negative thing, but it ends up being I1 plus I3 minus I2. And together we sometimes refer to these things as I enclosed. It's the current enclosed by the circle, and we can use a right-hand rule to determine if they're positive or negative. We can choose if they're going into the page, call that positive. If they're coming out of the page, call that negative. And this is Ampere's law, is what this is refers to as. Now, in order to show that it's the same, even if you displace the wire from the center of the path, takes calculus that's kind of beyond the level of what we use in this course, and we're not going to worry about it that much. So Ampere's law here. We'll just sort of take advantage of the result of the, and also to show that if you displace the current completely out of the circle, that you get 0 in that case, and it has no effect on it. And it's analogous to what we found with Gauss's law, where we had in that case the integral of E dot n hat dA ended up equaling the charge enclosed by this surface that we're integrating over divided by epsilon naught. It didn't matter, well, if a charge was outside of the surface, the Gaussian surface that you're integrating over here, it had no effect on it. It caused as much flux to go into the surface as it had coming out, and so you ended up with it not affecting the electric flux. Now, this doesn't happen to be related to magnetic flux. Flux would be the magnetic field flowing through or pointing through some area, and this, we're just tracing along a line, and so we don't have any area built into this other than area inside the thing, but we're not ever calculating the magnetic flux in this expression. You need an E dot dA to get flux, and we'll have B dot dA here shortly in the next chapter, but not just yet will we be dealing with magnetic flux. So anyway, some analogies between Gauss's law and Ampere's law there. And we can use this law sometimes. Actually, I don't always remember that the magnetic field of a long straight conductor is mu naught I over 2 pi r, but I can remember Ampere's law that the integral around a circular path or any path of B dot dl is mu naught I enclosed, and I can apply it to the situation of a long straight conductor like I've got here. And if I just remember, okay, B dot dl is going to end up being B times 2 pi r, and it's going to equal mu naught I, and then I can arrive at this expression and use that thing. Okay, but let's check out one. We have a cylindrical conductor of radius r equals 2.5 centimeters. So that'd be a pretty darn big conductor. 2.5 centimeters is just about an inch, so it's that much, and that's the radius of it. So it's going to be 2 inches in diameter. That's one big conductor. I'd hate to try to bend those wires on a winter day in Moses Lake and try to get them into a junction box. That would be a nightmare. Oh, I'll put a point on here. I can just draw myself a circle there to represent this wire and give it a capital R. and it carries a current of 2.5 amps along its length. It should be able to handle that current with absolutely no problem, because you can have a wire that's much smaller than this in diameter that handles that much current. And it's uniformly distributed throughout the cross section of the conductor. Okay, so we'll just imagine that the current here is going into the page, and you could put a whole series of evenly spaced X's all over this circular area here, and that would still work. Calculate the magnetic field midway along the radius of the wire, that is at R/2, and find the distance beyond the surface of the conductor at which the magnitude of the field has the same value. Okay, so I want to pick a spot that's about halfway out here and integrate along that path. Well, let's see. Looks like that hole will work. So here's my little R/2 circle. And if I integrate around there, the integral of B dot dl along that circle will equal B times the circumference of that circle, which is 2 pi times R/2, and that will equal mu naught times the amount of current that is enclosed by that circle. Okay, well, this thing I have to think a little bit about how to calculate the current that's enclosed by it. Since there's 2.5 amps of current that are evenly distributed across here, there's a term that we call the current density, which is current divided by area, and that's how much current is actually going through some area. But in this case, I can think, oh, okay, well, this little circle here is going to be some fraction of the total area of the wire, and it will have that fraction of the current flowing through it. And if I do a little bit of thinking about this, the area of that smaller circle, A sub small, divided by the area of the wire, well, that's just going to be the area of the wire is just pi capital R squared. The area of the smaller circle is A, or pi times R/2 squared. Area of a circle is just pi R squared. And that top thing ends up just being 1/4 of pi capital R squared, and I've got pi capital R squared on the bottom. That's just 1/4. And so this smaller circle is going to have 1/4 the current flowing through it that the bigger circle does. So the I enclosed, in this case, I'll have B times 2 times pi times capital R/2 is going to equal mu naught times 1/4 I. And I forgot what the question was on part A. Oh, calculate the magnetic field midway along the radius of the wire, that is at R/2. And so let's see, B in that case, this is just figuring out part A, is going to equal, these twos go away, pi times R. I'll have mu naught I on top and 4 pi capital R on the bottom. And so that's what the expression is going to look like. Now, how far out from the surface of the conductor will it be before the external magnetic field out here has that same value? Well, for that, I can imagine some loop out here. And it'll be out there at some radius, little r. And let's see, remember this circle right here is the wire area itself. This is just the area considered in the first part. And what are we going to do for that part B? Get a new piece of paper for one thing. Okay. I can again use Ampere's law to do this. I'll have the integral of B dot dl. This is going to be for some loop that's out here that has a radius of r. And again, let's see, with going in, if I take my b vector or my integral dl to be in a clockwise path here, I can pull the b outside the integral and I'll end up with b times the integral around the circle of dl, which just ends up with the circumference of the circle. So I'll have b times 2 pi r, but that will equal, well, I actually want this particular one to equal mu naught I over 4 pi r. So, but this will end up equaling mu naught just plain I. And so the b out here a distance little r from the center will be, no surprise here, we've used this expression a few times today, b times 2 pi r, but I want that to equal mu naught I over 4 pi capital R. So I want to know what value of r will make these two, little r will make these two expressions equal. Well, let's see, I've got mu naughts on both sides. I've got i's on both sides. I'll replace those with ones. I've got pi's on both sides. And now I've got 1 over 2r, 2 little r, is equal to 1 over 4 capital R. Cross multiply and I get 4 capital R is equal to 2 little r, or little r would equal 2 capital R. 4 divided by 2 is 2. So halfway out along the wire, I get a magnetic field that will be equal to 2r beyond or from the center, or 1 radius r beyond the surface of the wire. We didn't do it on this one, but they did it in the book. And it's to show that what does the magnetic field, how does the magnetic field within the wire change with increasing distance from the center? And we can use Ampere's law to figure it out again. The integral of b dot dl, which will equal b times the integral of dl, and for starters, we'll just let, well, dl is going to be the circumference of some circle in here. This time we're not going to nail it down to a particular value. We'll just say b times 2 pi r, and that will equal mu naught I enclosed, where we'll imagine here, I'll draw a new picture for this. There's our center. Whoops, that's not the way to do it. And I'll imagine that somehow here I've got a, okay, so here's some little circle of radius, little r, and it's part of and concentric with this long straight wire we have that has a radius capital R. And the current in the wire as a whole would just capital I, and I want to know how much is enclosed by this thing. And it's like what we did before. It'll be the fraction that this thing represents divided by, or the area of this thing divided by the area of this, times the amount of current we have. And that ratio of the areas gives me the fractional area that this represents compared to the total area of the wire. So if that makes sense. So anyway, it'll end up being mu naught. I would have pi little r squared divided by pi capital R squared times just the current. And so in the wire, so the V times pi r will equal mu naught little r squared over capital R squared times I. And if I divide both sides by 2 pi little r, I'll end up with the magnetic field looks like mu naught over 2 pi. And I'll still have a little r on top and a capital R on the bottom times I. And all of this stuff is just a constant for the particular situation we're talking about. Capital R is the radius of the wire. That would be just some number. Mu naught over 2 pi is just a number. The I is just a number. And what we see is that the magnetic field within the wire is equal to this constant, which is just a constant for the particular geometry we've got and the current. It's going to be increasing linearly as you go from the center of the wire out. And if you made a graph of that, you'd just see that it increases linear as long as you're within the wire. Once you're outside the wire, then it starts dropping off like 1 over r. And so it's got a curve to its shape outside the thing. And that's kind of interesting. The magnetic field is going to be at its strongest on the surface of the wire. It's 0 at the center, at its strongest on the surface of the wire. And I think that's something that shows up in superconductivity sometimes. In fact, I think we've got an example problem sort of like that. Okay, the next one's a solenoid. Let's skip it and come back to it. Oh, they both have to do with solenoids. Okay, we'd better deal with that. In the book, they go through some examples of using Ampere's law to figure out the magnetic field inside of a solenoid and also inside a toroid. And what a solenoid is a very closely wound coil of wire. Shoot, I've got one out in the classroom that's kind of like that, but you just have these coils all have the same common axis, and they're very closely spaced typically. You can have, even in a centimeter, if you're using fine enough wire, you could have hundreds of coils within just a 1 centimeter length. And usually they're layered as well. And with that particular combination, you can get quite a strong magnetic field inside the solenoid. And what you can do with that, what I do in the demonstration at school is I've got a steel rod that just fits inside one of the solenoids that we've got. And if I have, say, 4 amps of current flowing through that solenoid, the steel rod, I can pull it most of the way out to the bottom and have it hanging vertically and let go of the steel rod, and it'll get pulled right back into the solenoid. And there's a part of the starter system on cars called the solenoid, and it does something like that. It when you go to start the car, it puts a large current through the solenoid, and it pulls a shaft into it, and that shaft has a gear on one end of it, that matches up with some teeth on the flywheel of the car. The flywheel is a thing attached to the camshaft that, at least I think it's the camshaft, that it's got some gear teeth on the outside of it as well. This shaft that's pulled into the solenoid is being spun by the starter motor, and when its teeth mesh up with those on the flywheel, they'll turn the flywheel, which turns the engine, and that's how you start your car. Then you get stuff happening like pistons compressing a gasoline air mixture in the cylinders, and then you get to ignite that and start your car. And if your battery is a little bit dead where it doesn't have enough juice to turn the flywheel, or even to pull that shaft into the solenoid, then your car won't start. Then you have to do something else to start it, like maybe push start it, where if you've got a manual transmission, at least you get a bunch of buddies together, they all push on the car while you have the clutch pushed in with the car, the gear shift in a gear. You pop the clutch at some point, that will turn the engine. And so that's how you start the car. But anyway, solenoid, what do we do with something like that? Well, you imagine that you're looking at just a part of the solenoid, and maybe half of it, say, and you've got a whole bunch of wires that are all right next to each other that are all carrying the same amount of current. And these wires go in both directions a long ways. And so that's what you start with. And then you imagine you're going to, let's just suppose that these currents are all going into the page here. So we've got something like this. Then you imagine that you take a little walk around an Amperian loop, which is something that you might, a word that you might make up. We had Gaussian surfaces. Now we can have an Amperian loop. And we're going to take our walk in a direction where we'll go like this. Okay, we'll go in a clockwise direction around this Amperian loop. Well, the magnetic field inside here, because you've got a whole bunch of wires to the left and a whole bunch to the right, they end up canceling out those parts of the magnetic fields that don't point straight along. For instance, the wires over here will tend to have magnetic fields that point up like that. The wires over here will have magnetic fields at that point that kind of point down like that. And the up and down components cancel, and all you get is a magnetic field that points in this same direction. And so that's what you get. Outside of here, there will be not much magnetic field, because on the opposite side of these turns right here, you'll have turns where their magnetic fields are, or their currents are coming out of the page. The magnetic fields of these wires will tend to cancel the magnetic fields of these wires. And if you have the approximation of an infinitely long solenoid, they do end up canceling each other. Now, this is an approximation we're dealing with, but it'll give us a bit of an idea how strong the magnetic field can be inside of one of these things. So we go around our little length here. For this part, we'll have a length which the magnetic field is 0 out here. Inside here, as long as we're going along a path that's parallel to the axis of the solenoid, we'd expect the magnetic field to be uniform in strength and always pointing down the thing. So we'll imagine this thing has a length L. The B dot dl along these parts is 0. So our integral of B dot dl for this Amperian loop, we'd have to split it up into 4 integrals, but it's going to be 0 for this part, 0 for this part, and 0 for this part. The only part that contributes is just this little length here. And so this will end up being BL. Now that's supposed to equal mu naught I. Okay, I enclosed by this thing. Well, how much current did we get? Let's suppose that we have n turns of the current that are inside here. We'll end up with V is equal to, VL is equal to mu naught times n, the number of turns that we had within that, or no, they use a capital N, sorry. Don't want to confuse the notation from what's in the book. Or the magnetic field ends up equaling mu naught times N over L times the current. Actually, it's just plain the current that's in each one of those loops, not enclosed. That's this part. Okay, N over L is actually something that shows up in solenoids. It's the number of turns per unit length. So and we use a lowercase n to stand for that one. And so it's a pretty tidy expression. The magnetic field ends up just equaling mu naught n times I, and the n is the number of turns per unit length. So you get a pretty strong magnetic field inside of a solenoid by having a lot of turns per unit length. There's a little bit of a compromise between the current you can have flowing each one and the turns per unit length, because one way to increase the turns per unit length is to use skinnier and skinnier wires so you can pack more of them together, but then those can't carry as much current. So you'd have to figure out for your particular situation just what's going to be the best trade-off. Now we can try one of those other problems. If I can remember where I put them. Here they are. A closely wound long solenoid of overall length 30 centimeters, which is immaterial actually, has a magnetic field of 5 times 10 to the minus 4th Tesla at its center. That's not very strong. That's only about 10 times as strong as the Earth's magnetic field. And it's carrying a current of 1 amp. How many turns of wire are on the solenoid? Well, 30 centimeters is 0.30 meters. And so we're going to use that. Actually, we've only got 1 sig fig on everything here. So we'll just call it 0.3 meters. And the magnetic field, which they tell us, is going to be mu naught Ni. Pretty sure that's what I got. Yeah. Which is going to be mu naught times the number of turns it has divided by the length of it times I. And we want to know how many turns of wire are on the solenoid. So we want capital N. Well, let's see, that'll equal, N is going to equal B times L divided by mu naught I. And we'll get some number here. 5 times 10 to the minus 4th Tesla. But what were the units on a Tesla? A Newton per amp meter. And let me know if I got that wrong. Times L, which is 0.30 meters, divided by 4 pi times 10 to the minus 7th. Oh, great. What did I do with that sheet that's got all those constants on it? These things drive me batty after a while. Okay, here we go. Newtons per amp squared. And then the current is just 1 amp. So the only number we've got more than one significant figure on is this one down here, which we're going to have one significant figure anyway. Trying to see if I've got those. Yes, I do. Okay. Got this thing handy, the magnetic field, a Newton per amp meter. Good, I remembered it right. Okay, well, what are these things all going to combine to give me? I'll have a Newton per amp on the bottom. There's a Newton per amp on the top, so those divide out. And there's a meter and a meter. I'm going to be dimensionless when I get done with this. So that's good, because all it's representing is the number of turns of wire. And that should be a dimensionless quantity. So let's see. Pi times 4 times 10 to the minus 7th. Then I get something like about 120. Now that's actually 2 sig figs, so you could round that to 100 turns anyway, but in fact, maybe that'd be better. Consistent on our units. So that's how you would do that thing. That one's not too bad. This one might be more fun. Let's see. Some superconducting alloys at very low temperatures can carry very high currents. For example, something rather wire, NB, is that niobium? Or, I don't know. But it can carry wire at 10 Kelvin, can carry 10 to the third amps and maintain its superconductivity. So determine the maximum B field which can be achieved in a solenoid of length 25 centimeters if 1,000 turns of that kind of wire are wrapped on the outside surface. Okay, so B is going to equal mu naught Ni here. And this could be a hefty magnetic field. We'll see. 4 pi times 10 to the minus 7th. I forgot it again. For mu naught, newtons per amp squared. And 1,000 turns of wire over 25 centimeters. So, and the 1,000 is dimensionless. 25 centimeters is 0.25 meters. And then 10 to the third amps, 1,000 amps in each one of those wires. So we'll get a reasonably large magnetic field here. Well, it's going to be in the neighborhood of a Tesla anyway. I'm not sure exactly. 1,000 times 1,000 is 10�6. Divided by that's going to be 4 times 10 to the 6th. That's 4 pi times 10 to the minus 7th. So still only about 1/10 of a Tesla, I think. So maybe not as impressive as it looks. Somehow, let's see. Oh, 4 pi is more than, yeah, that drops us down to 10 to the minus 6th. So I do get something about 5 Tesla. Yeah, I don't know how many sig figs, especially on this thing. All we have is 1,000 amps. So 5 Tesla. Is it going to be a Newton per amp meter? Yes. Amps over amp squared is an Newton per amp meter is a Tesla. So That's a reasonably strong magnetic field. This is on the order of the strength of the magnetic field in an MRI machine. I don't know how much current they have flowing in those things. I've got a neighbor who actually works in the MRI machine clinic at Confluence Health. I should ask him sometime. I always wanted to do a field trip where we would go visit that thing, but I don't. This is not the time. People having medical techniques done just don't want classrooms of students walking through while that's occurring anymore. Not that you can blame them, but I always thought it would be neat to go learn about that thing because it's a neat example of magnetism at work. And it's it's an oscillating magnetic field. Nowadays, it's an MRI machine, which is magnetic resonance imaging. In the early days of the field, before it was actually a medical diagnostic technique, it was called NMR, which stood for nuclear magnetic resonance. And it still is nuclear magnetic resonance. They get the magnetic field to oscillate at a frequency that I think the nuclei of hydrogen atoms will resonate at. And so they can use that to map out the interior of the body. And but nobody wants a diagnostic technique with that word in it. So they changed it. All righty. Tomorrow, let's see. We looked at solenoids. I think I want to start looking at the next chapter, which has to do with, oh, no, maybe we'll look at magnetic materials tomorrow, which is the last section in 28.8, and talk a little bit about where magnetism comes from in ordinary materials, or sometimes not ordinary materials. And then our last section in magnetism will be chapter 29, which is on electromagnetic induction, that's where we'll start looking at magnetic flux. And, oh man, I've got some neat demonstrations out at school that, that show this. And maybe I'll run out there and try to film videos of myself, or I'll look on that set of demonstration videos I've got. There's one demo that's just really cool. That's pretty amazing. But anyway, tomorrow, the last section in 28. And then the rest of this week and part of next week will be chapter 29. And we'll have a test probably fairly early next week on the magnetism stuff. And then for the rest of the quarter, we'll be studying special relativity with a brief foray into general relativity. I want to talk about just what Einstein's general theory of relativity is and what sort of predictions it makes. We won't get to go on a field trip to LIGO this spring. They're still not having them down there. In past years, that's something that, boy, since 2001, I think we went down there every year until, oh, just a couple of years ago. It's gotten more and more popular as since they've discovered gravitational waves, and it's harder to get a field trip booked anymore. Used to be I could book the field trip in mid-May to go down there the first week of June, and now if you want a field trip in June, you have to schedule it in September, or pre-COVID you did anyway. But I would encourage you to go down there when they reopen for visitor field trips to check that out. It's absolutely astounding. And they would have, once a month, they'd have it open to the public. Okay, any questions? we're sort of closing in. We know what effect magnetic fields have on currents. We know how currents can produce magnetic fields. That's what the solenoid section is. Tomorrow we'll look at how magnetic fields can arise naturally in material. Something interesting to read about, but I don't know that they have it in our book, is how the Earth produces a magnetic field. I think it's in a small section somewhere. And other planets can produce magnetic fields. I've been watching a series of videos called Field Guide to the Solar System, and or a Field Guide to the Planets, I think is what it's called. And I'm pretty sure the woman who's giving the lectures is a geologist, because she talks a lot about minerals in geology. And I remember when I took geology as a class that you can get lost in the minerals. There's so many names for them. But anyway, she talks a lot about those, but also about how planetary magnetic fields are generated. And it's mainly convection currents of material in a liquid, like the liquid outer core of the Earth. And other planets have lost theirs. Mars had one at one time. It vanished with time because of the smaller size of Mars. Other planets still have pretty strong ones. Jupiter has a crazy strong magnetic field, and kind of interesting. You can look at Jupiter in radio emissions, and it's got this huge region around it that has very strong electromagnetic fields and shows up in a radio telescope as much larger than what you perceive of as the planet itself. So interesting stuff. Anyway, we'll stop there for the day, and I'll see you tomorrow. For the lab this week, I need to do a little bit of experimentation to see. I forgot to put something in your kits. I think I did. Did anybody get a little thing in their kit besides those other leads that I put in there? Something that you could attach to a 9-volt battery, snap onto the top of a 9-volt battery, and use that as a power source?
I don't think so.
Okay, yeah, I meant to get you
Probably
one,
just
and I'm pretty
tape them
sure I
or something.
forgot. Well, yeah, except what you can use is, we'll switch back to this thing. I'm pretty sure you've all got one of these little gizmos in there. And this is a power supply, and I'm going to experiment with it and see how stable it is. But you can plug this into a USB port, or you could buy an external power supply for this. And if I was going to experiment much with this kit, and I'm tempted to, I'd get a power supply that could just plug into here. And it'd be what's referred to as a wall wart. It's a little transformer you plug into the wall, and it produces DC current that can then go into here. And it says it can take VN 6.5 to 9 volts. So actually any little transformer that would do that. But on these other prongs that are poking out of this thing, you can connect some of your wires and use this thing to run experiments. And that's what I'd like you to do this week. I've got just a lab where you're investigating things using that. And I've got it mostly written up. I'll see if I can finish that thing off today and get to do some more electronics here the next couple of weeks. But that's where we'll go. Other than that, I'll turn you loose for the day and see you tomorrow.